The Peregrine Falcon hunts by executing a vertical dive, or stoop, at speeds reaching 380 kilometers per hour. But this creates an immediate physical problem. How does a predator moving like a speeding bullet hit an erratically dodging starling without overshooting its target? Usually, speed is the enemy of agility. The faster an object moves, the wider its turning radius becomes. This 3D model shows the starting conditions of the hunt. The falcon begins high above a starling, flying a straight baseline path below. At this high altitude, the falcon has zero kinetic energy, but a full reservoir of gravitational potential energy. The dive that follows is a strict physics equation. To secure a meal, the falcon has to weaponize that potential energy, converting it into kinetic energy to force an intercept. As the falcon drops into the acceleration phase, gravity takes over. To maximize that downward pull, the bird must strip away as much air resistance as possible. Notice the biomechanical shift required to eliminate this drag. The wings morph from a standard diamond shape into a tight vertical VTUK. This technical vector diagram maps the forces of that shape change. By tucking its wings, the upward drag vector shrinks significantly, allowing the constant downward pull of gravity to drive the bird toward its terminal velocity. But the prey rarely stays on a predictable path. The starling spots the predator and executes a sharp lateral jink. If the falcon remains in a straight downward tuck, it will miss the target entirely. To change course at over 300 kilometers per hour, what aerodynamic force must the falcon generate? Is it A, thrust, or B, lift, or C, drag? The answer is lift, specifically lateral lift. To catch evasive prey, the falcon must utilize the exact air resistance it spent the first half of the dive trying to avoid. Gravity provided the raw speed, but it also built the foundation for extreme agility. A higher airspeed means a massive volume of air is now rushing over the wings. This computational fluid dynamics simulation displays the velocity vectors around the bird during a dive. At terminal velocity, the airflow is so dense that even a microscopic adjustment to the wing contour drastically alters the surrounding air pressure. By slightly rolling its body, the falcon directs this massive aerodynamic lift force sideways, curving its flight path sharply to match the prey's evasion. That immense lateral lift allows a falcon diving at 300 kilometers per hour to pull up to 15 Gs of acceleration. The extreme speed of the dive is exactly what fuels its extreme agility. Generating turning force is half the equation. The falcon must know where to direct it. It tracks the line of sight rate. As prey evades, the line of sight angle changes. The falcon applies a navigation multiplier of 3, turning 3 times faster to plot a precise interception. In real time, the falcon's brain calculates the exact same proportional navigation algorithm designed by human engineers for guided missiles. The strike occurs, but immediately after securing the catch, the falcon faces a fatal problem. It is plummeting toward the ground at terminal velocity. This polar plot charts the pullout phase. The falcon flares into an open wing planform to survive. Looking at the top right at positive 37 degrees, this shape change spikes drag to brake, while simultaneously spiking vertical lift to flatten the trajectory. The entire hunting stoop relies on this 4-step sequence: establishing the high-altitude baseline, accelerating in the VTUK, tracking with proportional navigation, and surviving through the high-drag pullout. The stoop is a specialized mechanical strategy that converts gravitational potential energy into the specific aerodynamic forces needed to intercept a maneuvering target.